lesson 5.6. The last lesson in chapter 5.
Finally.
And it's really pretty quick. One big theorem we gotta talk about today. But first, warm up. Let's see how we did. Determine if the three sides could form a triangle. So number 1, they gave me 9 feet, 13 feet, 20 feet. As a review from our last lesson, the triangle inequality theorem says, as long as you can add two sides together, and their sum is greater than the third side, for all possible combinations of our sides of our triangle, then it will form a triangle. So I always start with my two smallest sides. You good, Tyler?
Yeah, I'm great.
Seemed like you tripped 4 times.
What?
Looked like you tripped on your feet about 4 times before you made it to your desk.
I got feet that are out.
Okay. So the two smaller sides worked. That's always a good sign. You do have to show all 3, guys. So first we tested is 9 plus 13 greater than 20. It is. And their combination, 9 and 20, their sum greater than the side of 13. You betcha. And then the third combination would be 13 and 20, the two longer sides. Again, feels silly that we have to show this, but that's what the triangle inequality theorem says. Number 1, you should have gotten yes. And number 2, if I start with my two smaller sides, you'd realize right away, 4 is not greater than 7. No. So that's all I gotta show is that one of the inequalities doesn't work, and that's not gonna form a triangle. Next one. Find the range for the measures of the third side of a triangle given the measures of two sides. Okay, so I showed you that I kind of use X to represent my third side, my unknown side. And again, triangle inequality theorem, I just have to show each side sum. So I'll start with 6 plus my unknown. That has to be greater than my other side, 15. That has to be greater than 15. Same as 15 plus my unknown side has to be greater than 6. And my two given sides, their sum has to be greater than that unknown side of X as well. Then you solve these inequalities. Here, just subtract 6 from both sides. I get X has to be greater than 9. Here, subtract 15 from both sides. I get X has to be greater than negative 9. We can kind of ignore that because if X has to be greater than 9, that's implying it's going to be greater than negative 9 as well. So you can kind of ignore that because according to this first criteria, it has to be greater than 9. So it's going to be greater than negative 9. All right, here, when I add those together, I get this statement. I showed you, I like to rewrite it this way. I didn't flip the symbol, I'm just rewriting that statement, and that tells me X has to be less than 21. So, X has to be greater than 9 and less than 21. Another way I could say that is in between 9 and 21. Could it be 9 or 21? No, just in between. So how we write that is our compound inequality, like this. That X has to be in between 9 and 21, not equal to, in between. Anybody 3 for 3 with those? Oh, these are just great. This one was a fun little problem, wasn't it? Number 4. According to the diagram on the left, circle the values that could represent X. Okay, so similar to the last problem where I'm going to set up my triangle inequalities that I know each two sides, their sum has to be greater than the third. So I'm going to set up all my possibilities here. It doesn't matter what order you do them. And then we solve. So I already know for my first inequality there that X has to be greater than 3. My second one here tells me X has to be greater than negative 3. That's implied here. Okay. Here, X has to be less than 11. So if you wanted to write this as a statement, you could. X has to be in between 3 and 11. So let's circle which possible values it could be. Could it be 3?
No.
5?
Yes.
5 is in between 3 and 11. 8?
Yes.
Also in between. 10?
Yes.
11?
No.
No. Can't be equal to 14?
No.
No. Okay. You guys are so smart. must have a great teacher. Just kidding. Okay. Do you guys know what a door hinge is?
Yes.
Probably.
Kind of looks like that, right? That's like the hinge on like the inside of the door. Okay. And you can picture this. I can like take this side of the hinge and kind of like open and close it, right? Okay. So we have something in geometry called the hinge theorem. It's kind of similar to like picturing an actual hinge. So let's connect this to geometry. It says, think of two segments A, B, and BC that are hinged at point B. Okay, so I'm going to draw this here. This is point B. So I have AB and BC that are hinged there at point B, and I can kind of open and close these line segments to make angle B bigger or smaller. I'm picturing it kind of hinged at that point. All right. Follow-up question says, as we make a bigger angle with the hinge, so with point B, what happens? All right, well, let's try to draw a picture here. Let's say I make that angle bigger. Now, you want to try and draw these still as like the same two segments. So maybe just like mark those are the same size, even if it's not perfect on your drawing. But we need to show I'm using these same two line segments. I'm just trying to make that angle bigger. So as this angle gets bigger, just like if we were to open up a hinge, and if I were to make this a triangle here, what would happen to that third side? What'd you say? It gets bigger. That's the hinge theorem. That as long as you have two congruent sides of two different triangles, or in like the same triangle, the bigger that angle is, the bigger that third side is going to be. Okay? The opposite side gets, in this case it was AC, gets longer. Okay. So let's go through kind of like the hypothesis and conclusion of the hinge theorem. What do you need first in order to use this theorem? So the hypothesis here is that as long as you have the two congruent sides, and we're looking at their included angle, so I have this nice visual here for you. They're showing you right here, AB is congruent to FG in that second triangle. So here's the hypothesis. If AC is congruent to FG, and a second side is congruent, in this case, AC is congruent to FH. So that has to be shown that you have like the two congruent sides, otherwise we can't necessarily say that these are being hinged or apply the hinge theorem. That would whichever two sides form a bigger angle, so it has to be the included angle, meaning the angle that these two congruent sides make up. Whichever one's bigger, their opposite sides the one across from the bigger angle is going to be longer than the one from the smaller angle. Okay? So as long as you have the two congruent sides and the measure of, in this case, of angle A is larger than the measure of angle F, then the hinge theorem allows us to conclude that the side across from the larger angle, which in my picture over there is BC, that side is going to be longer or larger than the side across from the smaller angle, which in that case was GH. Okay, make sense? That's hinge theorem. Not too hard. Guess what? The converse of this theorem is also true. The converse of this theorem. Now, in order to apply the converse, you still have to like show the green part works. still has to be two congruent sides, okay? So in this case, you can see here, JL and PR are congruent. In those two triangles, LK and RQ are congruent. Okay, so the converse, you know the side lengths. You know the third side length of the triangle. So the converse of the hinge theorem says, well, whichever angle is across from the bigger side is going to be a bigger angle. So in this case, if PQ is greater than JK, which it is, 12 is greater than 8, then the converse of the hinge theorem allows us to conclude characteristics about the angles. Then the angle across from the larger side, which is angle R, is going to be bigger or larger than the angle across from the smaller side, which is angle L. That's really the only theorem we're going to focus on today. We're going to do 4 example problems. You can picture this as just like using your hand, right? If you're talking about like hinging between like your thumb and your fingers, and you picture connecting my fingers as a third side, the bigger I open up this angle right here, the longer that third side is going to be. That's all it is. Okay. First example says, compare the measures AD and BD. Before I even start making any conclusions about the hinge theorem, I got to make sure that my hypothesis is met and that I have two congruent sides to these triangles, because there's two triangles here, triangle ACB and BCB. They're showing me these sides are congruent. Do I have a second congruent side? What side? Hey, that side's congruent to itself by what property? Reflexive. Reflexive. What did you say? Side against side. Okay. That's all right. That's not bad. I mean, we do have a side.
I saw a side and an angle on the side.
Yeah, exactly. But
First thing that came to
Matthew, are those angles congruent? No, so we can't prove the triangle's congruent. That's okay. I like your thinking. All right, reflexive property. These are not two congruent triangles. They're not two congruent triangles. So, this angle is included of the two congruent sides on that triangle. And this angle, 68 degrees, that's the included one on the two congruent sides for the other triangle, right? Okay, so the hinge theorem hypothesis is met. You have two congruent sides, and I have two included angles here. Now, sometimes, folks, you're not going to get this lucky where it tells you what these are. Sometimes it might tell you like this angle and this angle, and you have to do a little bit of math to figure out what the angles are. But it's nothing that you can't handle, because you know that all triangles have to add up to 180. Okay, and you know ones that lie on the same line are supplementary, all that good stuff. So just keep in mind, it might not always be this easy of a pitch. All right, so which angle is bigger, 70 degrees or 68? 70 degrees, right? That's a bigger angle. That's larger than 68. So the hinge theorem says the side across from the larger angle, which in this case would be AD, is going to be longer or larger than the side across from the smaller angle, which is BD. Is that a comparison of AD and BD? You betcha. By hinge theorem. Okay. That's what I had to do. Questions? Let's try one with the converse, where we know the side lengths, and they want us to compare. My smartboard has not been my friend today. We know the side lengths, and they want me to compare some angle measures. Okay, so here I have two triangles. They're showing me this side DC is congruent to this side AB. Do I have a second congruent side? Yeah, the one in the middle, the one shared side BD. Okay. They want me to compare the measures of angle ABD, that's this angle, and BDC, that's this angle right here. Now what I know is the side lengths of the side across from those angles. Of those two sides, which one is larger? AD, yep. I think you said 8. I was like, I don't see any 8. 5.5 is greater than 5. Yep, 80 is greater. So, which angle is going to be greater? ABD is going to be a larger angle than the one across from the smaller side, BDC. And that is the converse of the hinge theorem. Okay. 2 down, 2 to go. Classic examples. Let's take it a step further. Find the range of possible values for A. So I'm looking at my picture here. They're labeling 2 congruent sides, and then I have this shared side. So in my triangle on the left here, I have this included angle of those 2 congruent sides of 141 degrees. And in my triangle on the right, my included angle of the 2 congruent sides is 9a plus 15. And then I notice, all right, they gave me the measures of the sides across from those angles of that third side. And in comparison, I know 18 is larger than 16. So I know that angle across from side 18, 141 degrees, that has to be bigger than whatever 9a plus 15 is. This right here is a hinge theorem. Oh, my green marker wasn't working at all today. It just started working. All right, let's solve this one quick. So remember how we solve inequalities is exactly like equations. The only difference is if I ever multiply or divide by a negative, I got to flip my symbol, which that doesn't come up in this case. I get this statement, which I would rewrite this going this way. A is less than 14. A has to be less than 14. Okay, now we're not done. Because according to my answer here, A could be any number in the entire world that's less than 14. Could A be negative 100? 9 times negative 100 is what?
Negative 9.
What's negative 900 plus 15?
No.
Could that angle be negative 885 degrees? Could you have a negative 885 degrees in a triangle?
885.
No. We can't have a negative 885 degree angle in a triangle? You sillies. All right. So I like to call this the common sense theorem. I made this up. I didn't make this up. It's just I made up the name for that. Okay. All triangles angle measures are between 0. I know it can't equal 0, but it can be in between 0 and how many total degrees can't we go over in a triangle? 180. So negative 885 is not in between 0 and 180, right? All right. So hinge theorem's important. It gave me one criteria. A has to be less than 14. But I'm going to need to apply a little bit of common sense and what I know about triangles. That this angle, first of all, this angle has to be greater than 0, which means it has to be positive. This statement says that it has to be positive in math, right? It has to be greater than 0. Can't be equal to 0, just greater than 0. So let's solve this. I'm okay with you doing this as a mixed number or an improper fraction. I'm going to do improper fraction. This says, all right, it can't be every number less than 14. It has to be greater than -5/3 in order for us to get a positive angle. So we're like, okay, great. That makes more sense now. And if it was -5/3, 9 times -5/3 is -15 plus 15. That'd give me 0. And we could have a 0.0001 degree angle. We could. It'd be really, really tiny, really, really cute. But we could. Just has to be greater than 0. All right. The other one I got to set up is that it has to be less than 180. For example, I couldn't have 100. 9 times 100 is 900 plus 15. I can have a 915 degree angle in a triangle. By the way, you can have negative angles. You'll learn about in pre-calc. They don't exist in triangles.
But they should.
Okay, so this also has to be less than 180. So when you're doing these problems, you gotta throw in this little common sense theorem, okay? All right, let's solve this one quick. Okay, I wrote this as an improper fraction. What is this as a mixed number? 18 is 54 1/3. Okay. A has to be greater than -5/3, less than 18 1/3. But my hinge theorem says, hey, it has to be less than 14. So which of these criteria can I kind of ignore? This one right here, because this implies if it's going to be less than 14, it's also going to be less than 18 1/3. Does that make sense? This takes care of this statement. So my possible values for A would be anything in between -5/3 and 14. That was my answer. Don't let this throw you off that we can have a negative variable value. We can, because we have 9 times that plus 15 more, so as long as the angle measure comes out positive, you're fine. All right, one more like that, and then we'll call it a week. We'll call it a chapter, actually. That's nothing. This time, find the range of possible values for n. Okie-doke. I don't see any congruent sides other than this shared side. 8 and 8. Oh my gosh, you're right. 8 and 8. Those are congruent. Okay, good. Hinge theorem applies. Here's the included angle of those two congruent sides of this left triangle. 47 degrees. Here's the included angle of the other triangle. All right, let's look at their side measures across from those angles. I have a side measure of 9 and a side measure of 11. What's bigger, 9 or 11? Correct. 11 is greater than 9. So 7n plus 5, since that's my angle across from the side 11, is going to be greater than 47. Hinge theorem. All right, solve this quickly. Hinge theorem says the variable has to be greater than 6. Again, we got to put a little cap on this. I know this unknown angle measure has to be greater than what? 0. Good. Thank you, Matthew. Has to be greater than 0. Can't have negative angles. before I solve this, let's set up the other common sense one. This angle has to be less than what? 180. Thank you, Gwen. 180. You can't have measures that total up to 180 in a triangle. Alrighty, folks. Now we can solve these using our algebra skills. Alright, so the Hinge theorem tells me n has to be greater than 6. My common sense theorem tells me n has to be greater than -5/7 and less than 25. Which of these three can I ignore because it's kind of already reiterated? Yes, this one right here. Because if it has to be greater than 6, it's going to be greater than -5/7. So to write my final answer in my sandwich inequality, my compound inequality, I know n has to be in between 6 and 25. If you want to check your answer, plug in these numbers, and it should give you like your 2 extreme. Okay? Yes, sir.
So what if you did do -5/7 instead of 6?
It wouldn't fit the Hinge theorem then. It would fit the fact that yes, it has to be in between 0 and 180, but then you'd get a smaller angle than this one, and the Hinge theorem says since this side is 11, that angle has to be larger. Good question. Any other questions? Wasn't this a nice chapter? Okay. I have another question for you. Besides sharing my knowledge of